All right, so this lesson is on operations involving functions. Now, functions is something that a lot of people struggle with. They struggle with, I don't think it's necessarily what a function means, but the notation. I think it's how we write functions that people struggle with. And so you're going to want to pay attention to the notation because if you can understand the notation, it's really not bad at all. It's really, you'll see what we're doing is pretty simple. It's just a matter of knowing what it's trying to tell you. So first off, what is a function? So a function is a type of relationship, that should say of, not or, type of relationship where each input value has only one output. So if you plug in a number for x, there's only one possible answer you can get out. There's only one y value. So there's not two answers when you're solving. There's just one answer when you plug things in. And that's what makes it a function, is that for every input, there's one output. So we have equations, and some equations, if you plug in one number, you actually get two answers out, or you get more than two answers. And then some, you get one answer out. So not every equation is a function, but every function is an equation. So if we have an equation that is a function, instead of doing y equals, we'll use this symbolism, and this is read out loud as f of x. So it's an f parentheses x. So that's replacing y. And this f stands for function. And so it's basically function of x, where it's telling you what your input value is. So this notation is really nice if you are in computer science. If you're doing stuff in computer science, you write programs where you plug things into the program and then it outputs something. And these are actually a lot of what you're programming, what you're writing are called functions. You plug something in and then there's an output, and it will be written just as you see here. A lot of programming languages will have the name of the function, and then in parentheses is what you're plugging into that function. So sometimes it's parentheses, sometimes it's brackets. Each programming language has its own symbolism, but it's always the name of the function, and then after that is what you're plugging in. And that's exactly what this is here. Our name of a function here is just f. We're just naming it. And then what comes after that is what we're plugging into it. So if you're going into computer science, or you have experience with programming and writing functions, this should be very familiar. It's just seeing it from a math standpoint, but you've been working with functions. One thing that is very important to note is that this is not multiplication. We don't have two variables f and x. This is f of x. It's a very specific notation. So if you see anything that says f of x like this, the f parentheses x, that's not multiplication. You don't have an output of f. It's very specific. It means something very specific. So you want to always think of that this is a function that's just the same thing as y. So when we're working with functions, we have equations that are functions. You plug in a number for x. So you'll plug in something, instead of x on the left, it'll be like 5 or something. And then you plug that same number on the right side, everywhere you see x, you plug in like that number 5. But then anything you do after that, you only do on the right side. So when we're working with functions, we're basically only working with the right side, and we're evaluating most of the time or simplifying. When you plug in a number and then you follow the order of operations on the right, that's what we call evaluating a function. So that's what you're going to be doing a lot with functions, is just plugging in numbers and then following the order of operations. And when we do this, we just plug in the number on both sides, and then anything that you do after that is on the right. So we do have certain things that you can do to functions. Basically, you can add, you can subtract, you can multiply, you can divide functions. Just like you can add, subtract, multiply, and divide numbers, you can add, subtract, multiply, divide things with variables. You can do the same thing with equations and with functions. In week 8, and then if you go on to pre-calc, you'll actually learn about how you can add and subtract equations to solve systems. So, and there are some things where you'll be like dividing equations occasionally. I've divided equations when I've been trying to work with exponential functions. So what we can do to numbers, we can do to equations as well. The same rules, whatever you do on the left, you do on the right. That's, I mean, that rule holds for solving. Same thing when you're working with functions here. Whatever, if you're going to add the left parts, you got to add on the right. So when we do these things, add, subtract, multiply, and divide, and we're working with functions, they're called function operations. And they're basically, when you do these things, you're creating a new function or a new equation. So if you're adding two functions together, think of it adding two equations together, you now have a new equation as your output. And first we write what we're doing, and then everything we do after that, we do on the right. Just like with evaluating, I said you plug in your number on both sides, and then you just work on the right side. It's the same thing here, that you're only really working with the right side. So we've got these four things where you can add, subtract, multiply, and divide, and this is the notation for them. And this is where people get hung up, is they get really confused on the notation. So if you have two functions, this just means we have two different equations. One is called f and one is called g, or you can write it as f of x and g of x. These are our common names for functions. We start with f and then we go alphabetically from there. You can add functions together, and so the notation is on the left on these equations, and then on the right is what you actually do. So you're going to want to understand that what you see on the left is the notation, and then the right is what you are actually doing, that you're adding these things, or you're subtracting, or you're multiplying, or dividing. So when you see these things, you want to go back to the slide or your notes or whatever when you see this notation so that you know what it means. Basically, you're going to start with what you have written here, and then you start replacing your functions with what they're equal to, so you can start working with x. So this will make a lot more sense once we actually start doing things with functions. And all of my examples are working with the same two functions because there's a lot that you can do with it, and I figured that way we'll have some consistency. So we have two functions here. F of x equals x plus 3. So think of this as the same thing as y. Let me change my color. Y equal to x plus 3, because it's just another name for y. So we have an equation y equals x plus 3. And then we have g of x, which also you can replace g of x with y. We just have two different equations. And notice that when you have it with x and y, it's hard to kind of keep them separate because they both have x, they both have y. One reason why we use functions and use f of x and g of x is just so that they have different names. Instead of just saying, well, they're both y equals, you can call one f, call one g, and it helps you keep track if you have multiple equations. So that's one of the benefits of function notation. But we basically, it's the same thing as y. You've got an input and output. These are things you can graph. So on the left, we're finding the following. On the left, I have in parentheses f plus g, and then parentheses x. This is f plus g of x. So you want to take that notation and go to our chart here. We're finding the sum of a function. So what we're doing is this. So you want to first write this down, this formula that basically I have. So our formula on the left, we have exactly what they showed us. And then this is just f of x plus g of x. You're just adding the two functions together. That's what this is showing us. So now let me color code what we have here. So I'm going to say f of x is green. Actually a slightly darker green than I intended. And then let's say g of x is blue. So I'm going to just color code here. So I am replacing everywhere that I see f of x. So everywhere in green, I'm going to replace it with what f of x is equal to. And everywhere I see g of x, I'm going to replace that with what g of x is equal to. And we don't touch the left side. So on the right, I have f of x, and f of x is equal to x plus 3. So I'm going to write that as x plus 3. So I am just replacing it with the right side. And then I have my plus sign, and then g of x is equal to the square root of 1 minus x. So instead of writing g of x, I can write the square root of 1 minus x. So now I have written these two functions added together. Once you've done that substitution, then you try to simplify if possible. We don't have any like terms here that we can simplify because we can't really add a square root to an x or a 3 or anything like that. So this is as far as we can go. This is as simplified as we can get. And this is our answer. So when it asks you what is f plus g of x, this is what it's equal to. X plus 3 plus the square root of 1 minus x. So this works the same way on the right where you have subtraction. So the rule is if you see f minus g of x, this is telling you take your function f and subtract g of x. So if we color code again, I've got f in green and g in blue. Again, we're only touching the right side. So f of x is x plus 3. Then I have my minus. And whenever you have subtraction, you should put parentheses around what you're plugging in just to make sure that you're subtracting the whole thing. And this would give us minus the square root of 1 minus x. So you're just literally taking what our formula says for these operations. So you're just rewriting it, and then on the right side, you're replacing the function with what it's equal to, and then simplifying. And order does matter for some of these. So you can also see something like g minus f of x. And then that means instead g is first, and then you're subtracting f of x. So the order matters. With addition, order does not matter, but order matters with subtraction. So if I was to do the subtraction here for g minus f, g of x is the square root of 1 minus x minus, and then with subtraction, we put in those parentheses, and f of x is x plus 3. So I would need to distribute the negative through here to simplify this further. And so you'd have the square root of 1 minus x minus 3. So it's a different answer than if we did f minus g. It's order of subtraction matters. But what you're doing is you're just literally doing what it tells you to do. If it says to do g minus f, you take those two functions and you subtract them in that order. Are there any questions? Okay. So same functions again, just to make it easier. And on the left, we have multiplication. So f dot g, that dot means multiplication. So it means we're multiplying these things. And then on the right, we have division, or it's written as a fraction. So on the left, if you see f, and you could write it without the dot. You could just write fg. It's assumed that's multiplication. That is f of x times g of x. So if I color code again and use the same colors, that can help you kind of keep track of what you're replacing where. So I've got equals, then f of x. And when we're doing this with the multiplication, always put parentheses for both sides. And then g of x is the square root 1 minus x. So we put parentheses because you may have multiple things you were multiplying here. Like in this case, we could multiply the x by that square root and the 3 by the square root, that you can simplify that or multiply that out. It looks messy if you do that, because when you multiply something by a square root, it goes in the front unless it's in the square root. So it looks kind of messy. But often if you're multiplying functions together, you might be multiplying something that you can FOIL and get a quadratic. So you might then need to follow FOIL and multiply that all out so that you can simplify. For multiplication, the order does not matter. Now on the right, we have division, and division, the order does matter. So if it says f over g, you need to make sure you do it in that order. So that's going to be f of x over g of x. So it's basically exactly what you see, f over g. So that's what you're writing here. And then we're only touching the right side. So I replace f of x with what it's equal to, which is x plus 3 over, and then g of x is 1 minus x, the square root. And we'll just leave it like that. We won't try to get rid of the square root in the denominator or anything like that. It's a lot of work to do that. So we can just literally write it the way it is, like that. But so you're just taking the two equations they give you, and you're just writing them as either added, subtracted, multiplied, or divided. So it's really not too bad. The hardest part is just it's just the notation. That's all it is. And so I think if you make sure you have those equations written down so that you know what the notation means, and then color code so you make sure you're plugging in the right stuff, it makes it a lot easier, because then you're just basically saying, what do I have here? And now I'm replacing stuff on the right side. And for the quotient of functions, where you're dividing functions in the bottom here, we just have to know that our denominator cannot equal to 0. So that's what that provided by thing is, that we can't divide by 0, so our denominator can't be 0. So you just have to keep that in mind. So those are all doing function operations just with x. We can do them with numbers replacing x instead. So on here we've got f plus g, and then instead of x we have 5. What this is telling us is that x is equal to 5. So normally the notation would have x in parentheses, but that's telling you your input. So it's telling us what number to plug in. So it's telling us everywhere you see x, replace it with 5. So our normal f plus g would be f of x plus g of x. When you replace the 5, it is now 5 everywhere you see the x's. So that's one of the nice things about function notation is it's telling you what number are you plugging in. So everywhere you see x, it means replace x with 5. So we had done f plus g. That was x plus 3 plus the square root of 1 minus x. So everywhere we see x, we're replacing it with 5. Maybe I should color code this. So instead of x plus 3, it's now 5 plus 3. And then instead of the square root of 1 minus x, it's the square root of 1 minus 5. So you plug in those numbers, and then you follow the order of operations on the right. So when you're evaluating, it means you follow order of operations. So we've got 5 plus 3, which is 8, minus, and then 1 minus 5 is negative 4. So we have the square root of negative 4. So this is going to give us an imaginary number. We can pull out the I from the negative, and then the square root of 4 is 2. So we're going to get 8 minus 2i. And that's what it means to evaluate this particular function is first you write down what it means, and then because they have x being replaced with 5, everywhere you see x, you replace that with 5. And then you follow your order of operations. So on the right, we have f minus g of 2. So first I'll start with f minus g of x equals f of x minus g of x. And that's x plus 3 minus, and we already did this. That's why I'm reusing the same function. And now it's 2 in the parentheses instead. So everywhere I see x, I need to replace it with 2. So having like a pencil or something like this, or color coding, something to help you see that function notation is just telling us, well, what am I replacing? And what am I replacing it with? We're replacing x with whatever is in the parentheses. So 2 plus 3 is 5 minus, and then inside the square root, 1 minus 2 is negative 1. And the square root of negative 1 is I. So this is going to be 5 minus I. And that would be our answer for the subtraction of these functions. So second row here, now we've got multiplication and division. So our multiplication, f times g of x, was x plus 3 times the square root of 1 minus x. So I'm actually just going back to what we had here, the non-multiplied out, the non-distributed version. So instead of, since we already did it and I don't have a lot of space here, I'm just going straight to what our answer was from the previous slide. That was just those two functions multiplied together. And so here our x is negative 8. So I'm going to replace all of these x's with negative 8. And then I'm going to follow the order of operations on the right side. So negative 8 plus 3 is negative 5. And then I have a square root. 1 minus negative 8 is 1 plus 8. That's going to be square root of 9. So the square root of 9 is 3, and I'm running out of room here. So this is negative 5 times 3, and we get negative 15. Now on the right, we have our fraction. So f g of x from the previous slide was x plus 3 over the square root of 1 minus x. So we have f of g, and then in parentheses we have -3. So -3 is everywhere we see x. So you plug in those numbers, and then you're going to follow the order of operations. So -3 plus 3, we're going to get a 0 on top. And then in the denominator, 1 minus -3, that's 1 plus 3, that's the square root of 4. Well, 0 divided by anything is 0, so this is just equal to 0. Normally I would go vertically, but I ran out of room here, so should have put these on 2 different slides.
Hey, Stephanie, I have a question for you.
Go ahead.
On the top left example, I'm confused a little bit on where you got the 8 minus the square root of -4.
That should have been a plus.
Okay.
Thank you. As I look at that, I'm like, wait, you're right. That would be why you're confused.
Right, now it makes sense. Thank you.
Yep, you're welcome. Nice catch. I would not have noticed that had you not spoken up. So, do you have any other questions?
No, I'm good. Yeah, I really appreciate your time and showing me all this. So
cool. So the next thing that I've got for you, though, this might be the trickier part. And this is going to be domain and range with these things. So people struggle with domain and range to begin with because you have to use the interval notation, and people are not good at interval notation. When we have, actually, this is mostly just domain. I'm not even really worrying about the range. We don't care so much about range. So it's just the domain of these things. But when we're adding, subtracting, multiplying, or dividing, you have to look at the intersection of the domains, except for, oops, this is what I get for having a really busy day. This part aligns with the quotient. I'm going to have to redo my slides before I email this out tomorrow. I wrote that in the wrong spot. So you're always looking for the intersection except for the quotient when you're dividing, because you have to also worry about where you're not allowed to have the denominator equal to 0. So this is why when we were doing stuff with sets at the beginning of the class and we had those, the intersection and the union stuff, is because you need it for figuring out these domains. And domain is important when you have functions because that tells you what numbers you're allowed to plug in. If you're programming, you need to know, well, what numbers are going to be plugged into this so I can make sure that I've considered that my code can handle all of those cases. So that's basically, you're thinking about what possibly could be plugged into this function, or what numbers would we be putting in here, and that's the domain. So same functions again, because just a lot easier to work with the same functions. And so we've got the domain of the following. And so it's the intersection of the individual domains. So let me color code these again. So our domain, so f of x is x plus 3, which is a line. And lines always have a domain of all real numbers. Just every time. So that's something that you're going to want to just have a cheat sheet somewhere, so that way you don't have to look it up or try to figure it out. Just if it's an equation of a line, if you graph it, and it gives you a line, it's all real numbers. And actually, let me bring up Desmos so I can show you how to graph these things. So Desmos is my favorite graphing calculator. So you just click graphing calculator. And once it loads, so previously when you've been doing stuff with graphing, like last week, you would just do y equals. Desmos can handle functions. So you just type in exactly what you see, and it knows what it means, and it will graph it. And so you can see that f of x is a line, and lines always give us a domain of all real numbers. Now on the right, we have g of x, which is a square root. And the domain is a little trickier here. I'm going to just color code here. So the basic rule, if we're graphing something and you have a square root, you do not want to have imaginary numbers because we can't graph imaginary numbers. So whatever is inside the square root here, that has to be greater than or equal to 0. So I'm going to just kind of put an arrow down here. So inside the square root is 1 minus x. It has to be greater than or equal to 0 in order to prevent getting any imaginary numbers inside there. It could be 0 because the square root is 0 is 0. That's fine. We just can't have any imaginary numbers. So it's got to be at least positive. So I can solve this equation. So I can subtract 1 from both sides. And this is why we learned about solving inequalities. I have negative x is greater than or equal to negative 1. Then I can divide both sides by a negative to get rid of the negative in front of the x. And when I do that, the inequality symbol is going to change direction. And this will give us x is less than or equal to 1. So our domain, when we write this in interval notation, is going to be negative infinity to 1 with a bracket. So that's how we write anything that has like a less than or equal to a number. So we've got our two domains in interval notation. Now for both f plus g of x and f minus g of x, our domain, if we can get the right color, is the domain of f of x intersecting with the domain of g of x. And that's for both of these. So their domains are going to be exactly the same, even if the resulting function looks different. We're going to get the same domain for both because that's what the rule is that it's the intersection. And because we have the same functions for both of these, they're going to have the same thing. So I do this by graphing. So I have a number line. And I'm going to just put 0. I always put negative infinity and positive infinity on my number line. And then I'm also going to put 1 on the number line because one of our domains, that's a number that's involved with it. And so now I'm going to color code, and I'm going to kind of do it above. So our all real number domain means the whole number line is shaded. So that's basically what that's going to look like. The less than or equal to 1 domain means I'm going to have like a closed circle or a bracket, and then I'm going to be less than or equal to that. And so that's what it's going to look like. Now the domain of our function after we've added these together is the intersection. So you look to see where are these overlapping. So I have both lines drawn and they're overlapping basically everywhere less than 1. And then at 1, both of them include the value of 1. So that would be like a bracket or a closed circle there. So you're looking for where they overlap, and that's why I draw them on top of each other, because then you can kind of see that, okay, both of these are in the same area. So then you read your drawing here for your interval notation. So the left side is at negative infinity, which always has parentheses. And then my yellow is at 1 with a bracket, and that is my domain. And that is also going to be the same domain for the subtraction because we find the domain the same way. So the domain for the addition is the same as the domain for the subtraction. So you don't have to go through the work a second time because you'll get the same domain. Are there any questions so far on these? Okay. Now let's look at these with the multiplication and the division. So multiplication, this domain is the same as the addition and subtraction. So we've basically already found that. So we know that it's going to be negative infinity to 1 with a bracket. Now, the division is slightly different because it's that same domain, but then we also have to consider where the denominator is not equal to 0. So we have this f of g of x, which is equal to x plus 3 over the square root of 1 minus x. And we know that the domain of f is all real numbers. The domain of g was negative infinity to 1. And then we also need to worry about this denominator. So that square root of 1 minus x cannot equal 0. Because we can't divide by 0. So we have a third thing that we need to worry about here when we have the division. So that gives you an equation that you can solve. And we can solve it by, and this is why you had to learn how to solve equations with radicals. We had all these different types of equations we're looking at, and this is where they come into play. So to solve something with a not equal, that's the same thing as solving something with an equal. The rules are still apply, so you can square both sides. So squaring gets rid of the square root. We have 1 minus x. It's still not equal, and then 0 squared is 0. So now we're going to solve this equation for x. So I can just add x to both sides. And this gives us 1 cannot equal to x. So we are not allowed to have x because that will make the denominator equal to 0. We're not allowed to have the number 1 for x because it makes the denominator 0. So I'm going to draw my number line again, just like we did for the previous ones. Negative infinity, positive infinity, I'm putting 0, I'm putting 1. And so the all real numbers domain just means everything is graphed. We have our domain for everything less than or equal to 1. And now this third one says we're not allowed to have 1. So you can think of that as an open circle, but we can have everything else. Because all we know is that we can't have 1 in the denominator, but everything else works. So I'm kind of adding this as a third layer on my picture. So when I'm looking at the intersection, I'm looking for where all 3 of these things overlap. So we have overlap everywhere less than 1, but at 1, we don't necessarily have all 3 things overlapping. So like 1 is included in the green in the all real numbers. 1 is included in blue, but it's not included in orange. So all 3 of these, they'd have to both be included, but it's not included. So it'd be like an open circle here, because if it's not included on one of these, it can't be included for any of them. So if you prefer the open circles, you can do open circles, but that's also same thing as our parentheses with the interval notation. So because we're not allowed to include 1, that means we can't have a bracket at 1 because it's not included. So this means our domain for our division is -infinity to 1, but with a parenthesis instead of a bracket. And so it's almost the same as the domain of the other ones, but because we had to worry about the denominator, that changed the domain because we had to make sure that we didn't plug in anything that makes it 0. Does this make sense?
I'm learning.
The interval notation and the graphing, that's just something that a lot of people struggle with. So we can go back to Desmos here. I can put in the other function here, g of x, to get the square root. I just use that button. We got 1 minus x. So that's what the square root in blue looks like. And so at 1, it's graphed everywhere, and then it stops at 1. So that matches what we had here and what we solved, basically, is that it's graphed everywhere less than 1 or at 1, but then not after it. So I think we can even do, yeah, so if I turn both of those off, we can even do the function division here. What it's equal to is 1 divided by the other. And so you can see that this is 1 right here. And so what we got is that it's graphed everywhere less than 1. And so we can confirm that on the graph. Everywhere less than 1, we can see that we have this graph, but we don't actually have a value at 1. So it doesn't actually get to 1. This is, maybe I should actually put the line for 1 here. And then I'll make this dashed. So the dashed line is at 1. So we said for our domain, it's everything less than 1, but it doesn't include 1. And so you can see that it doesn't touch 1. And we can scroll up here, it's getting close to it, but it's never actually going to hit 1. This is something that we call an asymptote that you're going to learn about next week with rational functions. But it will never actually touch that line. So you can kind of use the graph to verify what we did with algebra here. And so if you're struggling with understanding domain and these number lines, you can kind of graph it in Desmos to get a different perspective to kind of look at it and understand what it means. So that could help. And Desmos is really nice that it does allow you to use function notation. And what's really nice with Desmos, if I go back to, say, one of these when we were, plugging in these numbers, let's say I do the bottom left with the multiplication. So f of -8 times g of -8. That's what that multiplication means. You can type it in and it will give you the same answer. And that's the nice thing about function notation is, oh, what if it wasn't -8? Maybe it was actually 7. I can just replace the numbers here and I'll get the answer. Function notation is wonderful for computers because instead of having to rewrite the equation all over again, all you have to do is change the number that you have plugged in, and then it will, figure it out. So let's say we want to plug in 10. There we go. It's really, really nice. So you can double check all of your function work in Desmos. You'd be basically writing what we have here, the f plus 5 plus g plus 5 thing. I don't know if Desmos does imaginary numbers, so let's see. No, Desmos doesn't like imaginary numbers because we can't graph it. And so it says undefined because you can't graph it. So you can't rely on Desmos for everything because it's only doing things in terms of graphing, but you can use it to kind of check your answers. And I
haven't quite read or finished reading 5.3 yet in the textbook, but so the G of X is kind of new to me. So basically it serves the same purpose as f of X?
Yes, it's just a different letter. It's so that you don't get confused. It's just a different way so you know that there's two different functions.
So we got more than one input then, in other words.
Well, the input's the same because you have an input for each different function, and we're plugging in the same number to both, but because there's two different equations, we've got the two different names.
Okay.
Yeah, so the book does kind of cover how in business you'll see R of X and C of X for revenue and cost. We tend to try to use letters that mean something, so that way you know what it's representing. It's not just some random letter. But it's like if you had, you name your kids so you can keep track of them. It's like we're naming our equations so we can keep track of them. That's all it is. And so you don't get confused about, well, which equation did I use here? Which Y did I plug in for? It just keeps track of all that for you.
I see.